We designed this telescope to see the very first galaxies that turned on in the universe, and when we saw what it did, I'm still trying to understand if we have galaxies in the dark ages. Let's get back to, they're not supposed to be there. So what has to give? Are the data? Is there something wrong with the data? Thanks to what the James Webb Space Telescope has seen, we now know that the world is not as old as we thought. The next thing we learn will make us feel stupid if we think we are that smart. The pictures coming from the Golden Telescope that people built are mind-blowing. These huge telescopes let us see back in time, even though it's only been 320 million years since the Big Bang. Now it takes many billions of years to create a galaxy like the Milky Way galaxy. To see it for yourself, there's no question about it now. The JWST has given scientists more questions than answers. To find those answers, they've come up with a lot of ideas. Some people think there are dark stars, and others think the universe is a lot older than we think. Come with us as we look at old galaxies that don't make sense and the most recent ideas that scientists have come up with. Will these ideas turn out to be true? Let's find out. It all began in July 2022 with the Deep Field picture. At the time, the JWST sent back its deepest infrared pictures, which showed an amazing view of the faraway universe. It also sent back the sharpest and deepest infrared image ever seen. Webb's first deep field shows the galaxy cluster SMACS 0723, which is full of thousands of galaxies, some of which are the smallest infrared objects ever seen. This deep field picture is a complicated mix of pictures taken at different bands over the course of 12.5 hours of exposure. Because it is so heavy, SMACS 0723 works as a gravitational lens, making some of the farther away galaxies look bigger. The galaxy cluster has a strong gravitational field that can bend light rays from galaxies farther away behind it, like how a magnifying glass can bend and twist pictures. A look at SMACS 0723 from 4.6 billion years ago is shown in the picture, which shows many galaxies in front of and behind the cluster. These galaxies gave off light billions of years ago, which lets us see some of the newest galaxies that were formed less than a billion years after the Big Bang. As the universe grew, their light got longer and longer until it reached infrared bands. Researchers have learned a lot about the masses, ages, histories, and makeups of these galaxies from this new data. This technology gives back a lot of information about each galaxy. The numbers show that light didn't hit Webb's mirrors for 13.1 billion years. This means that this deep field picture helped scientists find some of the oldest galaxies ever. We found a strange old galaxy called Maisy's galaxy, which was named after the discoverer's young daughter. This galaxy is a deep look into the very beginning of the universe. Maisy's galaxy is a big step forward in the study of the universe, even though it only looks like a bright orange spot. This fairly unremarkable spot in the sky is actually one of the oldest things in the universe. Scientists have now found out for sure how old the universe is at the point where Maisy's galaxy appears. Their results show that this cosmic being formed when the universe was only 390 million years old. In terms of the universe, this is very young. It is one of the 4 oldest galaxies that humans have ever seen. It was named for Stephen Finkelstein's daughter, who is 9 years old. He talked about how important it was that Maisy's galaxy was found. It lives in a time in the past of the universe that is so far away that we couldn't see it until the JWST came along. Finkelstein said this was the vast unexplored area where science still didn't know what galaxies looked like or how they formed before the JWST was launched. This was the case. The data from the telescope showed that Maisy's galaxy is one of the older ones. Because of how important it is, this amazing galaxy was given a unique name that sets it apart from the JWST's other discoveries in space, which usually have more official names like C1019, C2782, and CRS746. It puts young Maisy in the same group as famous scientists like Fritz Zwicky, Edward Jamari Stefan, and Carl Keenan Cipher, who all had galaxies named after them. Maisy, on the other hand, is special because she earned this award at the age of 9. Stephen Finkelstein found this galaxy in JWST data on the 9th birthday of his daughter. He joked that it was called Maisy's galaxy because he had always wanted a galaxy to be named after her. When it was time to share the results, the name stuck, and the galaxy was known as Maisy's galaxy from then on. Maisy is thrilled to have her name linked to such an important galaxy in the universe. But how do scientists figure out how old a star is? It's harder to figure out how old galaxies were in the early universe than it is to prove a birthday. It uses a number called Redshift to figure out how far away a galaxy is, how long its light has been traveling to reach us, and, as a result, what cosmic era we are in when we see it. Light waves of different lengths are called bands. For example, blue light has short wavelengths and high frequencies, while red light has long wavelengths and low frequencies. When light comes to us from a faraway source like an early star, that source moves away from us as the universe expands. There is less energy in the light from the source, so the bands get longer and change frequency. To put it more simply, blue light with a high frequency and short wavelength changes over time into red light with a low frequency and long wavelength. The name redshift comes from the fact that this change moves light toward the red part of the electromagnetic spectrum. It sometimes even gets to the level of infrared light, which people can't see. There is more redshifting of light when it has been moving through space for a longer time. Light from early galaxies like Maisy's has traveled for about 10 billion years before it gets to the JWST mirrors. So the light that left Maisy's galaxy was in the visible part of the electromagnetic spectrum. By the time it gets to the space camera, it has moved down to the infrared part. This is why the JWST is such a great way to study things that were around in the beginning of the world. Long wavelength infrared light is very easy for this space camera to pick up. In fact, it would have been very hard to find galaxies like Maisy's before the JWST. Even though the Hubble Space Telescope was great, it wasn't big enough or able to cover enough red colors to see galaxies that were so far away and had such a high redshift. At first, scientists thought Maisy's galaxy was about 11.8 billion years old based on how bright the pictures were and a few wide-frequency filters. To get a more accurate age, they looked at the spectral lines made by chemical elements at certain wavelengths with the JWST near-infrared spectrograph. It turned out that Maisy's galaxy had a redshift of 11.4. It's not as old as we first thought. In fact, it's tens of millions of years younger. Still, it's very old. The JWST took the picture only 390 million years after the Big Bang. Maisy's galaxy is unique and not at all like galaxies we see today. It would be different from galaxies like the Milky Way because it is much smaller. Things were denser back then, so galaxies were closer together and combined more often. Also, all the stars were very young because the universe was only 400 million years old. This made galaxies brighter and bluer than they are now. At the moment we're looking at it, Maisy's galaxy stands out because it's busy making new blue stars. This phase is known as starburst by astronomers. Even though Maisy's galaxy is very redshifted, it is actually bluer than we thought it would be because its stars are young, bright, and blue. There are a lot of stars in a blue ball shape. This also shows that Maisy's galaxy has fewer heavy elements, with hydrogen and helium making up most of it. It's surprisingly brighter than people thought early galaxies would be. This is a pattern the JWST has seen with other early galaxies it has observed. The mind suggests that stars may have formed more quickly and efficiently in early galaxies than was previously thought. This would have made the stars shine brighter and be easier to see. Finland wants to use the WST mid-infrared device to learn more about Maisy's galaxy. This will show more about its heavy element makeup and whether it has cosmic dust grains in it. It's easy to see that Maisy's galaxy is an early universe galaxy because it's bright. It's easy to study and measure things about it like its mass, shape, and heavy element content. It is one of many galaxies that help us figure out what happened in the beginning of the world. Maisy's galaxy used to be one of the oldest galaxies in the world, but that didn't last long. It's impossible to say enough good things about the JWST. In November 2022, just a few months later, NASA found even more very old galaxies, the most ancient galaxies ever. Scientists say that the JWST is showing us a whole new world that goes against what we thought it would be like in many ways. These early galaxies are very different from each other. In the astrophysical journal Letters, 2 research papers were released, led by Marco Castellano of the National Institute for Astrophysics in Rome, Italy, and Rohan Naidu of the Harvard-Smithsonian Center for Astrophysics and MIT in Cambridge, Massachusetts. These first results come from Webb's larger study project, which includes the GLASS and SE early release science programs. Researchers looked at the GLASS JWST pictures for only 4 days and found 2 very bright galaxies. These galaxies were formed between 350 and 450 million years after the Big Bang. Each one has a redshift of about 10.5 and the other 12.5. Just a few days after Webb shared its first data, scientists were shocked to find starlight from the farthest reaches of the universe. Scientists found a galaxy called GLASS Z12 that is very far away. It is thought to have started 350 million years after the Big Bang. Galaxy GNZ11 held the previous record. It was 400 million years after the Big Bang and had a redshift of 11.1. The Deep Sky projects at Hubble and Keck Observatory founded in 2016, these observations are mind-blowing and show that astronomy is entering a new age. One of the study's authors says these results are like finding a lost city during a historical dig. The very bright light from these early sources makes it hard for us to understand how galaxies form. We could have been wrong about how the universe began. Observations like these have led astronomers to agree that many galaxies in the early universe were much brighter than previously thought. This new information makes it possible for Webb to find more early galaxies in future scans of the far sky. Astronomers were very interested in these results because it is easier to see bright galaxies than faint ones. The time frame of our world has now been called into question. It looks like these galaxies started to form only 100 million years after the Big Bang, which is much sooner than anyone thought. The Dark Ages, the time in the early universe, could have ended much earlier if this is true. As an example of how old that is, these galaxies must have formed when the universe was only 1% as old as it is now. That's a very short time when you think about how old the universe is now, 13.8 billion years. One of the other team members said that measuring the forms of these early galaxies was surprising because it went against what most people thought about how the first galaxies formed in the chaotic early universe. This is because the shapes were calm and orderly, not scattered or disrupted. This finding was made possible by Webb's clearer infrared pictures. Astronomers saw that these galaxies are different from the Milky Way and other big galaxies we see today, just like they did with Maisy's galaxy. But there's also another puzzle. Scientists are not sure why the two galaxies these teams found give off so much light. They are considering two options. They could be very massive and have many low-mass stars like later galaxies, or they could be much less massive and have fewer but very bright stars called population 3 stars. These stars would be the first stars in the universe. They would burn at very high temperatures from pure hydrogen and helium, making heavier elements before stars use nuclear fusion to make heavier elements later on. We can't find these kinds of bright primordial stars anywhere in the nearby universe. This means they no longer exist, and the light we see from them is billions of years old, which makes them unique. The farthest source looks very compact, and the colors show that it has a population of stars mostly free of heavy elements. It may even have population 3 stars, but Webb's bands are the only ones that can provide solid answers. The infrared colors of these two galaxies are used to measure their distance from us. In the future, more spectroscopy measurements will reveal how light bends as the universe expands. These measurements will be confirmed by other measurements made in space. While we wait for these readings, the JWST has found even more interesting things like dark stars. The JWST finds more amazing things every day than just old galaxies. Scientists are shocked by the strange things they're finding with this tool. In August 2023, one of these findings took place. Scientists think they found something called dark stars. During this time, scientists don't even know for sure if dark stars exist. The idea was first proposed in 2007. Unlike regular stars, dark stars get their power from dark matter self-annihilation. Dark matter is an invisible substance that makes up 85% of the matter in the universe. Although more research needs to be done on these possible dark stars, they could change the way we think about how stars form in the early universe. Even though they're called dark stars, they're not exactly the opposite of the big plasma balls we know. It's interesting to think that dark stars could have given off 1 billion times more light than the sun and been 1 million times heavier. Although they've never been observed for sure, computer models show they might have formed soon after the Big Bang from clouds of pure hydrogen and helium falling inside protogalaxies full of dark matter. Researchers wrote in the Proceedings of the National Academy of Sciences USA that at least 3 faraway objects JWST had initially identified as galaxies might actually be single giant dark stars. This survey, also known as JADES, looked at these galaxies GSZ13, GSZ12, and GSZ11, which are the objects in question. If the finding is proven to be true, it will be a big deal. The study's co-author says it can't be proven for sure yet that these objects are dark stars, but they have traits similar to both dark stars and galaxies hosting fusion-powered stars. More observation time will be critical, and JWST technology might clear up this mystery. Another co-author hopes that one of these dark stars will be found during JWST's useful life. There are 2 possible ways the universe's first stars might have formed. Most people think these early stars got their power from nuclear fusion just like stars do today. But besides helium, they would have had almost no heavy elements because those elements hadn't formed yet in the early universe. These are the same stars from population 3 we mentioned earlier. But there's a different, more intriguing idea. In 2008, researcher Fries and her colleagues came up with an interesting concept. Dark matter might have powered the universe's first stars. The composition of this mysterious substance, which only interacts via gravity, is still largely unknown. In the early universe, dark stars might have come from helium and hydrogen clouds that were falling after the Big Bang. Many theories suggest that dark matter particles are unique because they're also their own antiparticles. All antiparticles share the same mass but have opposite electric or magnetic properties from their corresponding particles. The positron is an example. It's the electron's opposite, weighing the same but with a charge opposite to the electrons. When these two meet, they annihilate each other. If dark matter particles are their own antiparticles, when they collide, they annihilate. It would also cause particles to break down when they hit each other in these falling clouds. It may have set off a chain of particle interactions that led to the creation of photons, electron-positron pairs, and neutrinos. Neutrinos would have left the cloud because they don't interact with matter very much. Most of these particles would have stayed inside the cloud. The other particles would have given the hydrogen and helium their energy, which would have heated the cloud and helped stars form and grow. These stars would have looked like they were in the middle of small halos, early protogalaxies that formed about 200 million years after the Big Bang, before elements heavier than hydrogen and helium showed up. The main thing that made up these mini halos was dark matter, which made it perfect for these dark stars to form. This thick group of dark matter only existed in the early universe, which means that dark stars could only form during this time. Unlike their nuclear-powered peers, these stars stayed pretty cool and didn't give off the high-energy photons that stars usually do. Because of this oddity, they were able to keep gaining mass, which made them grow very big over the course of their lives. There are some strange things about these stars. The temperature of their surfaces is about the same as the sun's, but their brightness is a billion times greater, as bright as a galaxy full of fusion-powered stars. This idea beautifully explains another mystery that scientists are having a hard time figuring out. When these huge dark stars reached the end of their lives, they would have smashed into huge black holes. This could also explain the presence of some very old supermassive black holes seen in the universe. These black holes look too big to have formed quickly from population 3 stars that were powered by fusion. The researchers looked through the JWST collection of objects from before the universe was formed about 14 billion years ago to find these dark stars. Because there wasn't a lot of information about these objects' electromagnetic emissions, only 9 were thought to be good options. The features of 3 of these were very much like those of dark stars. They had a high redshift, which means they were old and came from a faraway place. They also seemed to come from a single source like a star instead of a galaxy that spread out. At this point, the researchers have only made a few observations of these objects, which means they can't do a more in-depth study just yet. An undeniable sign of a dark star's appearance would be a unique part of the electromagnetic spectrum where light is absorbed by a helium isotope that is only found in dark stars and not in galaxies. To find this signal, long-term observations are needed, which is not possible because the JWST is already being used for many other astrophysics studies. Early results, on the other hand, show that if these things were really dark stars, 2 of them would be about 1,000,000 times heavier than the Sun, and the third would be about 500,000 times heavier. The study team is currently working on an automated way to find more possible dark stars. Some of these may only need a short amount of time to be confirmed through observation. They expect to find a lot more possible prospects. If they could see a dark star directly, it would be a huge accomplishment. There are, however, other ways to find dark stars, such as looking for their fingerprints in the cosmic microwave background, CMB. CMB is a faint radiation glow that is left over from when the universe was very hot and young. Observing a dark star would not only give us new information about how the universe came to be but would also give us a unique chance to study how dark matter particles interact with each other. Seeing these kinds of events would help us learn a lot more about how dark matter works as a particle. Some scientists say that we were wrong about how old the universe is. Even though the dark star doesn't change a lot of what we already know about it, the age of the universe may not be as old as we think. We weren't kidding when we said that the JWST is changing how we think about the universe. We're finding things that go against what we know about the universe from a science point of view. The JWST found galaxies that are very old, just 325 million years after the Big Bang, but these galaxies have led cosmologists to come up with a bold theory. Some cosmologists say the world might be twice as old as we thought. Most scientists agree that the Big Bang happened 13.8 billion years ago, but Professor Rendra Gupta wants to change this. It might be 26.7 billion years old, according to him. But another cosmologist used the Sean standard, which says that claims that are out of the ordinary need proof that is out of the ordinary. So did Gupta have enough proof to back up what he said? Before we can understand his theory, we need to know how the cosmologist got these numbers. It's not easy to figure out how old celestial things are, let alone the whole universe. This guess depends on looking at the cosmic microwave background, CMB, radiation and taking readings of how fast the universe is expanding. The CMB only goes back 300,000 years after the universe began. It spread out into space and is the oldest radiation that we can see. Cosmologists figured out how old the universe is by carefully studying changes in temperature in the CMB. Edwin Hubble, a scientist, came up with Hubble's law in the 1920s, which adds to this. It finds the link between the speeds and lengths of galaxies and helps figure out how fast the universe is expanding. The Hubble constant is the name for this number. We can guess how long the Big Bang lasted by following this growth backward. On the other hand, Gupta's model looks at things in a very different way. It's based on the idea of tired light. Fritz Zwicky, a scientist, first came up with this idea in 1929. It helps Gupta understand why photons from faraway galaxies are redshifted. Now we know that redshift happens because the universe is expanding, which makes photons stretch. Photons lose energy slowly as they move according to the tired light theory, although this goes against what we know now. Gupta suggests that the redshift effect could be viewed as a hybrid effect that isn't just caused by expansion. If this theory is allowed to live alongside the expanding universe, there were galaxies in the first million years of the universe, but this is often called the impossible early galaxy problem. Scientists aren't sure why these very old galaxies formed so early on. Physics and observations make it hard to guess how old the world is based on what we know now. Galaxies need time to change over time, building up stars and structures in many ways. But powerful telescopes like JWST have shown us mature galaxies that formed when the universe was very young. This makes us think about how galaxies form and change over cosmic time. To answer this impossible galaxy problem, Gupta only suggests that the universe might be a lot older than it really is. Gupta also adds new factors that change over time. This means that galaxies were formed many billions of years ago instead of 100 million years ago. These facts make him think that the universe may be almost 28 billion years old. Scientists don't agree with this theory though. They say an easier reason could be that we don't fully understand how galaxies formed in the beginning of the universe. There are even people who think the phrase impossible galaxy problem is too strong. Scientists think that JWST observations do raise some questions about how galaxies formed in the early universe, but nothing is inherently impossible. Cosmology won't be changed much by Gupta's idea anytime soon, say experts. Our current understanding of the Big Bang and the expansion of the universe is based on a lot of observational data that has helped us explain many cosmological events. For Gupta's study to really take off, it would probably need more research and theoretical development. According to the standard model of physics, the Big Bang took place about 13.8 billion years ago. It has used readings from many places such as supernova data, observations of the expansion of the universe, and the distribution of galaxies. Scientists don't think Gupta's study is complete because it mostly looks at supernova data. We need to do strict tests in a number of different ways, but Gupta's idea has gotten a lot of attention from the media. Scientists, on the other hand, say this is just careless hype and question the scientific validity of the study itself. Any theory that tries to explain the Big Bang needs to take into account basic facts about the universe. It doesn't mean much to solve a new puzzle if it can't explain data that already exists. What do you think? If more study is done, could Gupta be proven to be true? Or is this just another theory that will lose support over time? Post your answer below and click like if you want to see more.